In this video, I will be checking just key technical points, many times not covered in technical reviews. The comments made here are also valid for the whole Rigol MHO98 family, or for any higher frequency budget scope above, let's say, 100 or 200 megahertz. I will be using two scopes for the tests. One is the MHO98 itself, and the other is an Agilent Keysight 300 megahertz unit. It's important to say that this is my first Rigol equipment. When I choose to buy Chinese measuring equipment, I normally buy from Sigland, and there is not a special reason why I do that. If instead you are interested in how to use the control panel or how to operate the Rigol MHO98 family, please refer to the two links below, redirecting you to a very nice channel that made a thorough review of this family of oscilloscopes focused on operation. Okay, let's do it. First of all, for higher frequencies, you will normally connect the scope directly to your DUT using a coaxial cable and terminating the cable at the scope side with 50 ohms. In regards to the probes, we will be talking about them in a while. There is one very important detail about higher frequency scopes. They should all include an internal switchable 50 ohm termination. But someone could say, I can always use an external through 50 ohms load. Well, now I will show why normally this may not be the best practice. I have here one generic through load, this one, let's see its focus, rated for 1 gigahertz, and another old one from Hewlett-Packard. And I will test them with this network analyzer already calibrated from 1 megahertz to 1 gigahertz with a high quality calibration kit. Let's start with the generic load. As you can see here, it's not very good. Now the HP load, much better. Let me zoom so you can see. It's much better than the other one. We are gonna use this one for our tests. Now I will connect the load to channel 1 of the MHO98 and check if channel 1 is in high impedance. Okay. And let's see what's happening. The network analyzer. Not very good, right? The impedance is all over the screen, far from 50 ohms. Now I will connect the network analyzer directly to the scope. And change the input so you have 50 ohms. As you can see in the As you can see in the network analyzer, much better, but this can be improved. We can include a 6 dB attenuator. At the input of the scope. And here we go. Much better. Well, just remember that doing this, you have to change the probe to 2 times, because the voltage here, when you include the attenuator, the voltage at the input will be half of the input. Now I will do the same test with the Agilent oscilloscope. Channel 1, high impedance. Well, you can see here that it's the same, right? Impedance is far from 50 ohms. Now I will remove the load and set channel 1 to 50 ohms. You can see there, let me focus there. It's much better. I didn't have to use the attenuator in this case. It's pretty good. And actually you should change the upper frequency to 300 megahertz. So the impedance is okay up to 1 gigahertz. 300 megahertz. You see? Very good. Well, it's the difference between a Keysight scope and a budget scope. Now about the probes. With care, you certainly can use the probe for lower frequencies, assuring that it will not load your circuit or add distortion to your waveform. Many times, the probes that come with the new scope doesn't even have the bandwidth of the scope, as is the case of the MHO98 that came with the 500 megahertz probe. In the case of the Agilent, the probe is for 300 megahertz, same bandwidth of the scope. Now let's see what your circuit will be seeing at the maximum frequency of the probe, which is the bandwidth, half the bandwidth and 1/10 of the bandwidth of the probe. The range of calibration of the network analyzer is 1 megahertz to 500 megahertz. In the case of the MHO98, the probes are a bit different from the standard we normally see. So I had to make an adapter in the lathe. Both the tip and ground diameters are different. Here is for the ground and inside there is another cylinder for the tip. Let me zoom a bit so you can see better. This is the probe of the agile. Let's first connect the network analyzer to the Rigol. Before that, let me check if the channel 1 is in high impedance and the probe is in 10 times. We have here 3 markers, one for the maximum frequency 500 megahertz, the other 250 megahertz, and the last one 100 megahertz. Here are the impedances in each of these frequencies. And now let me calculate the modulus for each of them. For 500 megahertz we have 14.5 and 3.15. So the modulus is 14.8. For the other ones I calculated before, and we have here 42.3 ohms for 250 and 112 ohms for 100 megahertz. Not too high, right? Now let's check the edge length. I have changed the frequencies in the network analyzer off camera. Oh, let me connect here. The channel 1 is in high impedance, and here we have the result. Here are the impedances. I have already calculated the modulus, and we have here for 300 megahertz 19.2 ohms. For 125 megahertz 76.6, and for 30 megahertz 1/10 of the bandwidth is 325 ohms. Okay, well, it's this scope goes only up to 300 megahertz, so it's not much different from the other probe. There are 3 figures of merit for modern oscilloscopes, and you probably already heard about them. I'll be measuring 2 of them in a while. BW, or bandwidth, rise time, and sample rate. Many times I hear or read someone say, why do I need a high frequency scope if my clock signal has no more than 100 megahertz? Well, the answer is simple. We live now in a digital world, and to see, for instance, a decent square wave or pulses, you need at least the 5th harmonic of the fundamental frequency of your waveform, or 500 megahertz. In short, if you think you have a 1 gigahertz bandwidth scope, in fact, you have just a 200 megahertz scope. Let's now analyze, for instance, this other waveform. The frequency is 1 kilohertz. But certainly you won't need just a 5 kilohertz bandwidth scope. Remember that in the last case I said square wave, which is not the case now. In this case, we will have to check the second figure of merit, rise time, and how rise time is related to bandwidth. And this is the formula normally used. The constant K will depend on the shape of the frequency response of the scope after the cutoff frequency, Gaussian or maximally flat, as known as brick wall response. Each of them have advantages and disadvantages. Modern digital scopes normally have the brick wall response. And here are the two types, Gaussian and brick wall. This picture was borrowed from Rod Schwartz's presentation. The last figure of merit is the sampling rate. Often disregarded, the Nyquist sampling theorem not only says that the sampling frequency must be at least more than twice the maximum frequency component in the signal, but also that the samples must be equally spaced. You certainly won't have to worry about that if you bought a Rod and Schwartz Keysight or Tektronix oscilloscope, but this could be a problem in some low-cost oscilloscopes, as it won't be easy to reach the inside guts of the scope and try to probe that. You can always externally test the limits of the scope to check its quality. The fact is that for a couple of reasons, noise, number of channels and so on, the sampling frequency will normally be many times the BW of the scope. In the MHO98, the sampling rate is 4 gigasamples per second, and it's valid for just one channel. And this is one of the reasons of its low cost. When you use more channels, the sampling rate will go down till 1 gigasample per second if you are using the 4 channels simultaneously. In my case, this won't be a big problem because for higher frequencies, 9% of the time I will be using just one channel. Comparing the MHO98 with the Siglent SDS5104X, 4 channels, 1 gigahertz BW, 5 gigasamples per second, the latter has a price of almost 5 times the price of the MHO98. To test the BW of the scopes, I'm gonna use my trustworthy generator from Roda und Schwarz and a power meter of the same manufacturer. So let's check the quality of this generator. I set 300 megahertz here, 0 dBm, and you can see down here, practically spot on. Now let me change the frequency to 1.2 gigahertz. 1.2 gigahertz, and you see that the level is practically the same. Now let's check the purity of the generator with a spectrum analyzer. I set here 300 megahertz, 0 dBm. Let's see what's happening at the spectrum analyzer. This is a delta marker. We have here minus 42 dBmc. for the second harmonic, and the third harmonic is about 10 dB below the second harmonic. Now I will change the frequency to 1 gigahertz. And change the settings of the network analyzer. Frequency start 500 megahertz and stop 10 gigahertz. So you can see that the 1 gigahertz carrier is pretty clean. Okay, let's start measuring the PW of the Agilent scope. I set the generator to 100 megahertz. The distance between lines here, I hope you can read here, is 300 millivolts. So 70% of 300 millivolts is 210. So let's Let me increase the frequency of the generator. And let's see. The frequency is 430 megahertz, well above the 300 megahertz limit. Pretty good, right? Now the BW of the Rigol generator is 100 megahertz. The distance between lines again is 300 millivolts, as you can see here, delta Y, and the internal impedance is 50 ohms, the same of the Agilent, but I included in the input a 6 dB attenuator, so the generator you'll be seeing a nice 50 ohms termination. Now let me reduce by 210. To 209.3, and let's increase the frequency. Oops. $100, $110. Okay, 0.7, and let's see the generator. So above the 1 gigahertz claimed, 1.162 gigahertz. Well, that's pretty good as well. The level of the signal in the scope had a bit of a variation, not too big. Again, we have to consider that the Agilent is 300 megahertz and this one is 1 gigahertz. And finally, let's test the minimum rise time the oscilloscopes can measure. For that, I'm going to use this pulse generator here, produced by a small British company. The rise time claimed is 30 picoseconds, but in fact it's less than that. It's a useful device to have in the lab. Okay, let's test first the Agilent oscilloscope. Input impedance must be 50 ohms. And as we can see here, we have here about 940 picoseconds. If we divide 0.4 by 540 picosecond, we get 425 megahertz, which is pretty close to the BW we just measured. Now the Rigol. Let's one to 1, 50 ohms, and the average rise time is 380 picoseconds. 0.4 divided by 380 picoseconds is 1.052 gigahertz, which is also very close to the measurement we did with the RF generator. So, answering the question, which is the title of this video. Yes, it was worth it, at least in a first analysis. It can be used decently as a monochannel 1 GHz scope, has a nice human machine interface, and came with a bunch of extras that are sold separately and would cost more than the price of the oscilloscope itself. Logic analyzer probes, 500 megapoints of memory upgrade, 200 megahertz arbitrary waveform generators, and a bundle of triggering applications. I hope the video helped somehow. Thanks for watching.